Welcome back. Today we are going to talk about the k-epsilon model, starting the average continuity equation and the momentum equation, which is given by this. Where this can also be converted in terms of Reynolds stress, but we are not going to do this for now. Using the Boussinesq approximation, we wrote that this term in the Einstein's notation is equal to this. Let me revise what we have done so far. In the zero equation model, we approximated nu t using analytical equation, which is the Prandtl model. We merged this term, which is the turbulent kinetic energy component, to the pressure, and the modified pressure is p bar plus 2 by 3 rho times k. In the one equation model, we assumed that there is another variable nu tilde, which is fv1 times the turbulent viscosity, and for this we use a transport equation, and we call this the Spalart-Alamarus model. In the k-epsilon model, which is a two equation model, we have two equations, one for k and another for epsilon. K is the turbulent kinetic energy and this is turbulent dissipation. We can compute the turbulent viscosity using the formula nu t is equal to c nu times k square by epsilon, where c nu is a constant which is always set to 0.09. And the transport equations for turbulent kinetic energy is given by this. Minus epsilon, and for the dissipation we write where pk is a production term and all other terms are constants which people do not change. We are not going to discuss the values of these particular constants because these are already set in OpenFOAM and you can always edit them. If this much is understood, then we should discuss that how do we set boundaries. We have added two variables, k and epsilon. We should know that how we set the values of k and epsilon. K is set using this formula, which is 3 over 2 u times I whole squared. So I is usually set as 5%, which is 0.05. So using this, let's calculate this for our case, which is 0.05 whole squared, which is equal to 0.05 times 0.54 whole squared, and then this times 1.5, which is equal to 1.0935 times 10 to the minus 3. And epsilon is calculated using c nu to the power 3 over 4 times k to the power 3 over 2 divided by L, where L is 0.07 times the characteristic length, which is h in our case, which is equal to 0.07. H is 1 for our case. Therefore, we will get this to the power 1.5 times 0.09, which is c nu to the power 3 over 4, this divided by 0.07, which is equal to 8.488 divided 10 to the negative 5. And from this we can estimate the initial turbulent viscosity, which is equal to c nu times k square by epsilon, which is equal to 0.09 times 1.09 into 10 to the minus 3, 935 divided by this whole squared, 8.488 into 10 to the power negative 5. We'll get 0.09 times 1.0935 whole squared divided by 8.488. This times 0.1 factor is 0.1. From this we'll get 0.001267. We'll save these numbers for simulation. Now let's talk about the y plus value. The y plus is close to 1 for LRMS model. But can we use this same y plus for k epsilon model? Notice that epsilon is approximately equal to 0 at the wall. So the turbulent viscosity, which is this c nu k square over epsilon, will tend to infinity at the wall. So if we use this same model to approximate the turbulent viscosity, our solution will struggle to converge because dissipation is going to be very high. This is not what we want. Therefore, for k epsilon models, the y plus should be in the range of 30 to 100. And to approximate the behavior close to the wall in the viscous sublayer and in the log region, we use wall functions. The wall functions for epsilon is given by c nu 3 over 4 k 3 by 2 over kappa times y, and this is called epsilon wall function in OpenFOAM. Similarly, for the turbulent viscosity, this is used. Nu t is equal to kappa times y times the friction velocity. This is also computed analytically. For the turbulent kinetic energy, we assume that it is constant close to the wall. We call this the Newt wall function in OpenFOAM. For k, we call this kqr wall function. There are other options for the turbulent viscosity, which is called Newt u wall function. Now we'll edit the simulation that we have done for Spalart LRMS model and then use it to simulate the same problem using k epsilon model and see what are the changes that we observe. We'll continue the simulation in the next lecture. Thank you.